Okay, so next we will be discussing about JFET. Previously, we discussed about BJT, which is known as bipolar junction transistor. Now, JFET is another type of transistor, but this is known as field effect transistor. Now, what does the word field mean? Field is nothing but voltage. Okay, so this is actually a voltage controlled device in contrast to the BJT, which is actually current controlled device. So here, the advantage is that you don't need an extra current bias. Okay, so that is one advantage of JFET. Now, this is one of the most simplest type of field effect transistor. From this, there are other different types of transistors which are currently used. MOSFETs, അങ്ങനത്തെ കുറേ transistors evolved. Okay, so these are also this BJT similar to your JFET, similar to your BJT, is also a 3-terminal semiconductor device. Okay, now these transistors, they are usually electronically controlled switches or resistors, or they are used to build amplifiers. Okay, now they work on the principle of depletion mode. Now you know what is a depletion region. What is a depletion region? Depletion region is a region which does not have the charge carriers. Okay, now when you think about your diode, you see that when the P and the N junction is brought close together electrically, what happens is that the P region has holes majorly, and the N region, they have majority charge carriers as electrons. Okay, so when the P and N region comes close together, what happens is that there is a junction that is formed. Okay, now you might have studied diffusion. Diffusion is nothing but flowing of something from higher concentration to a lower concentration. So same way here, diffusion of charge carriers occurs when the junction come across. Okay, so electrons from N region flow across the junction to holes and they combine. Okay, so once they combine, the place where the holes and electrons have left, they are depleted. They don't have any charge carriers. So that particular region is known as depletion region. Okay, so this JFET, what they do is JFET and MOSFET, they all work on the principle of depletion region. That is, there is a channel through which the current passes through. Okay, and that channel length or the amount of current is controlled by adjusting the depletion region. Okay, so that is the major principle of JFET. So the construction of JFET is for usually there is a substrate region. Okay, so substrate region is known as the major channel. Okay, so the channel can be N-channel JFET, which has a P-type material in an N-type substrate. Okay, so N-type materials are used in P-type substrate to form a P-J-channel FET. Okay, so usually the construction is done using a long channel of semiconductor material, and wherever you require these terminals, you provide ohmic contacts. Ohmic is nothing but metal contacts. Okay, a PJFET, the channel is P. Okay, what happens is the positive charge carriers are holes. Okay, so if the JFET contains large number of electrons, that is known as a N-type JFET. Okay, so you can understand the channel is N. Okay, so this is the construction in detail, where you can see the clear figure. So you can see the 3 terminals. You have source, drain, and gate. So gate, it has 2 terminals. So total you have 4 terminals for a FET. Okay, but overall, when you say you have only 3 terminals, the source, the drain, and the gate, and the current flows from the source to drain. Okay, and the controlling is done by the gate to source. Okay, gate and source. Fine. Okay, so you can see the yellow region, the yellow, the fluorescent yellow or green, whatever you can call, that is the P-type material, and the violet region is the N-type substrate. So the N-type substrate, that constitutes the major area. So you can see the channel or the major charge carriers are electrons. Okay, so this is an N-channel FET. In contrast to the N-channel JFET, so you can see the symbol on top. You can see the symbol on the top. So there is an arrow inwards, which indicates the conventional flow of current, showing that the gate region is a p-type material and the source and drain are n regions. Okay. Then second, you can see right to that, you can see a p-channel JFET. So in contrast to the n-channel JFET, the construction is like, say, you have a p-type substrate on which the n-type material is diffused. Okay. So you can understand that the major charge carriers are the holes for a p-type p-channel JFET. Okay. Looking at the symbol, you can see the conventional flow of current is from positive to negative. So you can see the source to gate, the arrow is shown outwards to gate. Okay. So how does the JFET work? So it is almost similar to the garden hose pipe that you use at home. Okay, imagine that the pipe is connected to the tap. Okay, the hose is connected to the tap, and you have turned on the tap, and at the mouth of the pipe, you are not applying a pressure. So what happens is that the water will flow uh, without any pressure. Okay, the water will flow. But slowly, if you try to apply pressure on the mouth of the garden hose, what happens is that the amount of flow of water is slightly restricted. So if you have applied the whole force, that is, you cover the entire, you can see that the amount of water has minimized very much. Okay. So when there is no pressure applied, you can see that you had free flow of water. Same way here, when there is no, I told you that the gate is the person which is controlling. When there is a gate source voltage, that gate source voltage is a person which is controlling the channel. Okay. So the same example of garden hose you can apply here. When there is no voltage applied across the gate and source, what happens is that there will be a smooth flow of current from the source to drain, provided that drain source voltage is applied. Okay. So from a drain to a source to drain, you can have a smooth flow. But imagine you are applying a voltage at the gate source. Okay. So in positive polarity, there won't be any change because that is the maximum channel that you can have. Okay. But if there is a reverse polarity, that is, you make the gate and source reverse biased. So here, when you're talking about an n-channel JFET, you have a p-type gate and n-type source. So the gate is given a negative voltage with respect to the source. What happens is that it makes the channel narrower because the depletion region tries to become widened. Okay. So hence you can see that, you can understand that. So let us see the diagram. Okay, you can see the diagram. You can see the first case. Okay, this is the first case when there is no gate source voltage applied. So what you can see is that this is the channel. This is the channel. Okay. So you can see that you have a maximum width, and when there is a drain source voltage applied, there will be a free flow of electrons from source to drain at the maximum. But imagine we try to control the channel. What happens is that the gate source voltage, if the reverse biasing increases, what happens is that the depletion region tries to move inside, thereby restricting the channel. So you can see the channel width has reduced to a particular extent where minimum current will flow. That is known as the pinch of voltage. Okay. So at the pinch of voltage, there will be minimum flow of current. Okay, it's fine. Okay, so this is the VI characteristics. Okay, VI characteristics in the sense our operating, we are controlling using gate source voltage. Okay, sorry. Yeah, we are controlling using gate source voltage. So this particular graphs are taken in such a way that your gate source voltage, you keep it at a constant and you vary the VI in the sense the drain source voltage, and you note the current. Fine. Okay. So what happens is that, let us say your gate source voltage is 0. Okay. When the gate source voltage is 0, where there is no gate source voltage applied, we have seen that you have maximum current flowing through. Okay, so initially when the drain source voltage is rising, okay, when you are increasing one second, when you're increasing the drain source voltage, this x-axis is the drain source voltage and this is the drain current. Okay, so when the drain source voltage is increasing, what happens is you can see the current increasing ohmically. Ohmically in the sense it follows the Ohm's law linearly. You can see it flows linearly, and once it reaches a knee voltage, the current flow is steady, no matter how much you increase the drain source voltage. That is the saturation region. Okay, so I'm telling you, we are discussing this particular graph only. Why? Because we are keeping the gate source voltage constant, because gate source voltage is the controlling factor, and we are understanding the different regions. Okay, so after a particular voltage, it remains in the saturation region. After that, if the voltage is increased further, there is a breakdown voltage at which you can see this is the breakdown voltage of VGS is equal to 0. After that, no matter what voltage you apply, the current tends to increase rapidly, or this is known as a breakdown. Okay, so this breakdown voltage is at a higher VDS for VGS is equal to 0. Why? Because you have a much larger channel. When you give much reverse biasing, you can see that the breakdown voltage, the drain source voltage required for breakdown is reduced more. Okay, so this is the VI characteristics of JFET.